So our speaker today is Josefina Vallejos, and her title, as you can see there, is Quantum Subgroups of SLQ2 and Roots of Unity of Arbitrary Order. Please, Josefina, go ahead.
Okay, so first, thanks Willy and Gisela for the invitation. So today I will talk about quantum subgroups of the quantum group SLQ2 at roots of unity of arbitrary order. This means that the parameter Q is a root of unity. This is joint work with Gaston Garcia and is part of my PhD studies. So let's start with a notion of what a quantum group is. We know that we have a correspondence between algebraic groups and commutative Hopf algebras. That is the following. If we have an algebraic group G, we can consider OG, that is the function algebra over G. And this is a commutative Hopf algebra. It has a structure of Hopf algebra. And if we have function algebra over some group G, and we compute the spectrum that are the algebra maps from OG to C, then we obtain again the algebraic group G. And the subgroups of G corresponds to the Hopf algebra quotients of the function algebra over G. Okay, what happens with the non-commutative Hopf algebras? Here we have a quantum group. We don't have a definition for a quantum group as a geometric object, but we know that there is a correspondence with this thing here, that is the deformation of the function algebra of G, and is a non-commutative Hopf algebra. So the quantum subgroups of a quantum group corresponds to the Hopf algebra quotient of this thing, that is the deformation of the function algebra of a group G. So the main problem is, given a quantum group, find all the quantum subgroups. That is the same to find all the Hopf algebra quotients of OQG. And we are interested in what happens when Q is a root of unity. So the strategy is give a construction of the quotients using exact sequences of Hopf algebras. Today, first I will show the results for SL2 and Q a root of unity of odd order. That is a result by Eric Müller. And later I will show our results for SL2 and Q a root of unity of even order. That this is our work with Gaston. So let's start with the definition of an exact sequence of Hopf algebras. So suppose that B, A, and H are Hopf algebras, and we have this sequence. So this sequence is exact if the first morphism is injective, the second one is surjective, the composition is the co-unit, the kernel of pi is the ideal in A generated by this B+, that B+ is the ideal of augmentation. The definition for the B+ is just the kernel of the co-unit. And B is the subalgebra of co-invariants under pi of A. Okay, and if we have a sequence of Hopf algebras, then this H is isomorphic to this quotient. Okay, here we are using that the kernel is the ideal generated by B+. Okay, some definitions. What is the function algebra over SL2? is the commutative algebra generated by these four functions that the functions are defined by the matrix coefficients. This means that xij of some matrix A is just the aj entry. And satisfy this relation. We have also the definition for the function algebra of PSL2, that is also a commutative algebra and is generated by these monomials by all the products of two generators of SL2. Okay, so now the deformation. OQSL2 is so now we will work with complex numbers, okay? Our field will be C. So OQSL2 is the C algebra generated by these four elements, A, B, C, and D, that satisfy these relations. So we can see that if we put Q equals to 1, we obtain the classical function algebra OSL2. But if Q is different from 1, we have a non-commutative Hopf algebra. Okay, and as I said, we want to use exact sequences of Hopf algebras to find the quotient, to study the quotients. So the first question that we ask is if OQSL2 fits into an exact sequence of Hopf algebras, and the answer is yes. Okay, this element fits into an exact sequence of Hopf algebras like this, where B is isomorphic to the function algebra over some algebraic group. And again, here we have the quotient that is isomorphic to OQSL2 over OQSL2 and B plus. Okay, so if we can find what is the subalgebra B, then we can compute the ideal of augmentation and we have the quotient. That's the idea. And what is the benefit of working with exact sequences is that we can study the element in the middle using the elements at both sides. And here we have a commutative and classical element. So in the following lemma, we will see what is the subalgebra B in each case, and it depends on the order of the root of unity. So for the first one, suppose that Q is a root of unity of odd order. This is a result by Brown and Goodall. Then we can consider the subalgebra B generated by these four elements, A, B, C, and D to the power of L. And this subalgebra is isomorphic to the function algebra over SL2. For Q equals to -1, we can do the same. Take the subalgebra generated by A squared, B squared, C squared, D squared. In this case, when Q is equals to -1, the order of the root is 2. So we can take the subalgebra generated by these four elements, but in this case, this is not a Hopf algebra. So we need to add these products for B to be a Hopf algebra, and this B is isomorphic in this case to the function algebra over PSL2. And if Q is a root of unity of even order, then we can consider the subalgebra B generated by these monomials, x to the power of m and y to the power of m, where x and y are generators of OQSL2. And in this case, again, B is isomorphic to the function algebra of PSL2. Okay, so in the case when the root has odd order, then B is isomorphic to OSL2. Here B is isomorphic to OPSL2. And here B is isomorphic to OPSL2. And what is the isomorphism in each case? So only for the first element, x11. In the first case, we are sending x11 to a to the power, we are sending x11 to a to the power of L. Recall that if I denote x, I'm talking about commutative elements, and A, B, C, and D are non-commutative elements. In this case, we are sending x11 just to A. And in this case, we are sending x11 to A to the power of N. Okay, this is the isomorphism that we are taking. Okay, so now for the three cases, odd order Q equals to -1 or even order, we know what is the subalgebra B. So now we can compute the ideal of augmentation, and we have the what is the quotient and what is the exact sequence in each case. And this is in the following theorem. Okay, so the first result is given by Eric Müller. If the order of Q is odd, we have this exact sequence where this element is the dual of the Frobenius-Lustig kernel. I won't give the definition of this here because the only thing that we care is that it's isomorphic to taking the quotient by the augmentation ideal. And we have this quotient here. For Q equals to -1, we obtain this exact sequence. Here we have OPSL2, and here we obtain just the group algebra of C2. And when the order is even, we obtain this exact sequence. Here we have OPSL2, and here we have the double dual of the Frobenius-Lustig kernel. Again, I won't give the definition of this. The only thing that we care is that it's isomorphic to taking this. Okay. So now we have the exact sequence for the three cases. I will start with the odd case, okay, that this is a result by Eric Müller. So we have a bijection between Hopf algebra quotients of OQSL2 and odd subgroup data that here is the definition, okay? I will use a similar definition for this for the even case, okay? So I will explain this with more detail in 5 minutes, okay? But let me say that a subgroup data is a collection of elements. Here we have two sets that with these sets, we have a subalgebra of SL2, a least subalgebra of SL2, and a subgroup of SL2. N is a subgroup of this thing where S is this, so S can be 1 or 0, okay? So it depends on the choice that we make of these two sets, if we have a subgroup here or not, okay? If S is equals to 1, we will have a subgroup, but if S is equals to 0, we don't have this part. This gamma is a group with an sigma that is the inclusion of the group into L, that recall L is a subgroup of SL2. And we have this delta that is a group morphism between the subgroup N, and the group of characters of gamma. Okay, so as I said, I will explain this later for the even case, but just for you to know, this is the result for the odd case given by Eric Müller. And there is a bijection. This means that any quotient is given by some subgroup data. Okay, what happens for the case when Q is equals to -1? So recall that O minus 1 of SL2. In this case, we have this exact sequence. Here we have O of PSL2, and here we have the group algebra of SIP2. And we have this theorem for the quotients of O minus 1 of SL2. So suppose that A is a quotient of this, then we have two cases. Or A is isomorphic to this quotient, that is the quotient by the ideal generated by the kernel of this sigma transpose, where sigma is the inclusion of a group into PSL2, a subgroup into PSL2. Okay, so for different subgroups of PSL2, we can compute the kernel of sigma transpose, and we will have a quotient. Or maybe A is isomorphic to a function algebra over some dihedral group. Let's see an idea of the proof. So suppose that A is a quotient of O minus 1 SL2. So by a result by Eric Müller, we know that this A is contained in an exact sequence like this. And we know that this diagram is commutative. So here we have that H is a quotient of the group algebra of SIP2. And this B is isomorphic to the function algebra over some subgroup of PSL2. Okay, so the thing is that as H is a quotient of SIP2, we don't have too much possibilities. Actually, we have only two possibilities. So let's see both cases. So first, we will use this notation for the inclusion of gamma into PSL2. Then the sigma transpose is an epimorphism between O PSL2 and O gamma. So the first case is if the quotient of SIP2 is all SIP2. In this case, again, by a result by Eric Müller, if we take the quotient by the kernel, the ideal generated by the kernel of sigma transpose is this one, we take the ideal generated by this kernel, and it's contained in an exact sequence of Hopf algebras like this, okay? So what we have is that we have the same diagram, but with A. Okay, so we can prove that these two things are isomorphic. Okay, so it follows that A is just isomorphic to taking this quotient. This is the first case. The second case is if the quotient is just C. Then we have that the epimorphism is given by the co-unit. And again, we have that this diagram is commutative. And as here we have the field C, then as this sequence is exact, then these two things are isomorphic. Okay, so then A is isomorphic to the function algebra over gamma. So what we have to do now is to find gamma. And as I said, gamma is just the spectrum of the algebra A. So we have computing this, and we obtain that this gamma has to be isomorphic to some dihedral group of order 2n. So let's see this with an example. An example of the first case, that is taking a subgroup of SL2, taking the inclusion, and computing the kernel of the sigma transpose. So we are taking sit n, the subgroup of PSL2. We need to find the inclusion of sit n into PSL2, but it's easier to find the inclusion of sit 2n into SL2. Okay, we can think about this inclusion. And we have the following diagram that is commutative. Okay, so using this inclusion, we can find the inclusion of sit n into PSL2. Okay, and dualizing this diagram, we obtain here the sigma transpose that we want. So we have this commutative diagram. Here is the sigma transpose between O PSL2 and O sit n. So now we need to compute the ideal generated by the kernel of sigma transpose. We have found that the kernel of sigma transpose is generated by these elements. And we have found that B and C belongs to the ideal generated by sigma transpose. Okay, so B and C are 0 here. Okay. So what we have here is that as B and C belongs to the ideal generated by the kernel, here B and C are 0, then we have that here A times D is equals to 1, okay? Because the relation of the determinant, that is AD minus QBC equals to 0, but if, equals to 1, but if we are saying that B and C are 0, then we have that AD is equals to 1. Okay, so as B and C are 0 here, we have only one generator, A, because D is the inverse of A. And it's generated by only one element, that to the power of 2n is equals to 1. So we obtain that this quotient is isomorphic to the group algebra of SID2n. So SID2n is a quotient of O minus 1 of SL2. And to finish the case -1, we have this proposition that says when two quotients are isomorphic. So suppose that we have two subgroups of PSL2, gamma 1 and gamma 2, and we have the inclusions gamma 1 and sigma 1 and sigma 2. So we have gamma 1, a subgroup of PSL2, and gamma 2, a subgroup of PSL2 with inclusions sigma 1 and sigma 2. So we say that these two quotients are isomorphic as quantum subgroups if there exists some row here from gamma 2 to gamma 1, such that this diagram is commutative. Okay? In this case, if we have this commutative diagram, then these two quotients will be isomorphic. Okay, so now the even case. So for the even case, we will have the same as the odd case, that we have a bijection between the quantum subgroups and an even subgroup data. So here I will give the definition of what is an even subgroup data. Again, it's a collection of elements such that the first two sets define a list of algebra of SL2, a subgroup L of SL2, and a subgroup L bar of PSL2. such that the Lie subalgebra has a positive part, a zero part, and a negative part, and the positive part or the negative part can be zero. It depends on the choice that we make of these two sets. This N, again, is a subgroup of this thing where S can be 1 or 0. So in some cases, we will have a subgroup, and in other cases, we will not have a subgroup. And it depends again on the choice that we make of these two sets. Okay, gamma is an algebraic group that is included in L bar, and the sigma is the inclusion. And we have a group morphism delta between the subgroup N and the group of characters of gamma. So with this definition, again, the theorem is that when Q is a root of unity of even order, there is a bijection between Hopf algebra quotients of OQSL2 and even subgroup data. So, what is the strategy to prove this theorem? First, the construction. If we have a subgroup data, we want to construct a quotient AD of OQSL2, and we will do the construction in 3 steps. And later we will see that they are all the quotients that we have. This means that every quotient of OQSL2 is given by some even subgroup data. Okay, so first the construction. If we have an even subgroup data D, there exists a Hopf algebra AD that is a quotient of OQSL2 and fits into an exact sequence like this, where here we have the function algebra over gamma. Moreover, we know that this AD is the quotient of this OQL, where recall L is a subgroup of SL2, by the ideal generated of the kernel of sigma transpose and the quotient by some J delta that is generated by some group elements, some group-like elements. I will show this later. What is this? And the thing is, this diagram is commutative. So, as I said, with these two sets, we can define a Lie subalgebra L, a subgroup L of SL2, and a subgroup L bar of PSL2. This is the first step. The second step is to take gamma, a subgroup of L bar, and taking the ideal generated by the kernel of sigma transpose, where sigma is the inclusion of gamma into L bar. This is the second step. And the third step is using N and delta to have one more quotient. And this is the quotient by this J delta. Okay, so let's see what is all these things that we are saying. So the choice of these two sets corresponds to take the quotient by the ideals generated by B, by C, or the ideal generated by B and C. Okay, so taking quotient by these ideals, we can construct a Lie subalgebra of SL2, a subgroup of SL2, and a subgroup of PSL2. And we will have this commutative diagram. Let's see what do we have in each case. So, case 1, what happens if we take the quotient by the ideal generated only by the element B? We will have here we will have, so OPSL2, and we have to take the quotient by all the monomials that has the term x1, 2, okay? That is the pre-image of the element B under this inclusion. And recall that this element is OQSL2, and the quotient by A to M minus 1, BM, CM, D to M minus 1. Okay, so, as we are killing B here, B has to be 0. Okay, so here, here we will have OQSL2, the same as we have here, but instead of B to the power of M, we have to kill B. In case 2, we are taking the quotient by the ideal generated only by the element C. So it's actually the same. Here we take the quotient by all the monomials that has the term x to 1. That is the pre-image here of C. And here we will have, instead of C to the power of M, we will have C, because we are killing C in this side, and this diagram is commutative. And in the third case, we are taking the quotient by the ideal generated by B and C. So here we have to take the quotient by all the monomials that has the terms x1, 2 and x2, 1. And here in the quotient, instead of B to the power of M and C to the power of M, we will have B and C. And again, using the determinant and that B and C are equals to 0, then A times D is equals to 1. So D is the inverse of A. Okay, so this is isomorphic to the group of algebra of set L in this case. Recall that L is equals to 2m, okay, is the order of the root. So this is the first step. The second step, we need gamma, a subgroup of PSL2. We take the inclusion of gamma into PSL2. And we will, okay, here. The second step, we will take the quotient by the ideal generated by the kernel of sigma transpose, okay, as I said. And again, by a result by Eric Müller, this quotient fits into an exact sequence, and we have that this diagram is commutative. Okay, and the third step. The third step is, we can do this, the third step only when we take the quotient by the ideal generated by B and C. Okay, because in this case, we will have that A is a group-like element. Okay, a group-like element is an element such that the coproduct of G is G times G. And what happens when, the coproduct of the element A is A times A plus B times C. So if we say that B and C are 0, then we have that A is a group-like element, okay? And if A is a group-like element, then in this case, we have one more step, that we will send the group-like elements of OQSL2 to the group-like elements of the function algebra of gamma. So we consider N a cyclic subgroup of set L. So suppose that N is generated by some P. And we can define this delta that goes from N to the group of characters of delta, okay? And why we take the group of characters here? Because they are the group-like elements of, this is the group-like elements of the function algebra over gamma. Okay, so now the last step is to take the quotient by this ideal. Okay, so as I said, we send the group-like elements of OQSL2 to the group-like elements of the function algebra over gamma. So we take the quotient by this ideal and we obtain the commutative diagram that we want. Okay, let's see this with an example. So again, we will take sit n as a subgroup of PSL2. The same inclusion that in example 1. By the same computation, we can find what is the kernel of the sigma transpose that is generated by these elements. And again, if we compute this quotient that is generated by only one element, again, A times D is equals to 1 if we put B and C equals to 0. But in this case, remember that the isomorphisms send x1 to A to the power of m. Okay, so as here we have x11 to the power of 2n, here we will have A to the power of 2 and n equals to 1. So we obtain this commutative diagram. First we kill B and C, and then here we do the quotient by the ideal generated by the kernel of sigma transpose, and we obtain this commutative diagram. But as I said, if we take the quotient by the ideal generated by B and C, we have one more step. That is, okay, suppose that n is generated by the element 2. So we want to send A to the power of 2 to some character of sit n. Okay, and in this case, the characters of sit n are just isomorphic to sit n. So the last step, we take the quotient by sending A squared to the generator of sit n. And we obtain this diagram. Okay, here this is the last step. And the benefit of this is that we can express the quotient, the quantum subgroups, with generators and relation in this way. Okay, so this was the construction. Now we want to prove that they are all. This means that every quotient of Hopf algebras is given by some even group data D. So let's start with a quotient of OQSL2 by a result of Eric Müller again. This A fits into an exact sequence, and this diagram is commutative, where this K is isomorphic to the function algebra over some subgroup of PSL2, and the sequence is exact, so we have this. And what we will try to do is to fit two more exact sequences in the middle. So for the first one, we take, we have that gamma is an inclusion of PSL2, so we take sigma as the injective morphism. And we know that this H is a quotient of this. So if we take the dual of H, this is a sub-algebra of the Frobenius-Lustig kernel. So with this information, we can find what is the Lie subalgebra, what is the subgroup of SL2, and what is the subgroup of PSL2 such that this diagram is commutative. And the last step is now we have the sigma transpose. So again, we can take the quotient by the ideal generated by the kernel of the sigma transpose. Then we know that this diagram is commutative. Okay, so now we want to fit this exact sequence here in the middle of these two exact sequences. And what we have here is that H, this H, is a quotient of U2 of this element. So we have that this diagram is commutative, that this is what we want. So if this W is the identity, as we have here identity and here identity, we know that these two things are isomorphic. So we know that A is isomorphic to this, that recall, this is just OQL, the quotient by the ideal generated by the kernel. But if W isn't the identity, we have one more step, okay? That is to prove that A is isomorphic to this quotient, okay? Again, we have to take the quotient by this ideal that we send a group like of OQSL2 to a group like of O gamma. Okay, so the case when W isn't the identity is the case when this is isomorphic to the group algebra of set L. So we can say that the kernel of W is just the group algebra of some subgroup of set L. So N is some set T. So we have that T of AP. This means that if here we have A to the power of T, and we apply T, we will have an element here that is a group like. So this element is a group like of the function algebra over gamma, that, as we said, this is the character group of gamma. Then we know that this element is the generator of the group of characters to some power. So we can define this delta and consider this ideal. Again, by a result by Eric Müller, we know that if we compute this quotient, it fits into an exact sequence like this, okay? And we can prove that this thing, this ideal is 0, and that all these things is just isomorphic to H, okay? And this is what we want. Recall that here we want only the function group of gamma, and here we want H. So this is what we obtain. Here we have H, and here we have only the function algebra of gamma. Okay, so that's all. Let me say what we are doing now, okay, the work in progress. Now we are trying to find the quantum groups of SLQN, okay? We have the quantum subgroups of SLQ2, but we want to see what happens for SLN. When Q is a root of unity of even order, the odd order is also done by Eric Müller. And we are also trying to define a Frobenius map between the UQSL2 and USL2, the enveloping algebras of SL2, when Q is of even order. So what happens here for the odd case, we have that UQ of SL2 is in UQSL2. And here we have U of SL2. For odd order, we know that we have this exact sequence. So if we apply the dual to this exact sequence, we obtain OSL2, OQSL2, and here the dual of this thing. That is the exact sequence that I have shown. But for the even order, we have the O part. I mean, we have this thing. And we want to prove that this is the dual of an exact sequence like this. But for this, we need to define what is this Frobenius map. And so we are trying to define this. Okay, so that's all I want to say.
Okay, thank you very much for a very nice talk. I have a silly question going back to the end of the case when Q was -1.
Yes.
There was a lemma on when gamma 1 and gamma 2 produce the same thing, and there was a rho, and sigma 1 and sigma 2. And before the...
This one?
Yeah, this one. So doesn't this exactly say that the image of gamma 1 and gamma 2 are the same in PSL2? So they are the same subgroup. They may... So the fact that...
Yes, it's saying that. Yes.
Yeah. Okay, yeah. I thought that this is a very complicated way of saying that they are the same subgroup.
Yes.
Okay. Yeah. I announced that it was a silly question. So are there any other questions from the audience? Let me see. Okay, otherwise I shall stop the recording here.